Hello students, in this video we're going to learn about maxima and minima. I'm talking about local maxima and local minima, and also stationary points, points of inflection and everything. Okay, so let us start. Okay, consider this, look at this diagram, students. Now you see here, you see a part of a curve y equal to f of x here, and you have the Cartesian plane, and you can also see that I have there's a point here. There's a point here which is nothing but 3, 8, which basically means f of 3 equal to 8, isn't it? Okay. Now, if you take any value close to 3 and find f of x, how will it look? I mean, will it be equal to 8, or will it be less than 8, or will it be more than 8? Let me just cross check. Let's say I take a point here. This is something, let's say 3.5. Okay, I want to find the f of 3.5. So what I'll do is I'll draw a vertical line. Okay, and I'll draw a horizontal line. So basically this is f of 3.5, isn't it? Okay, as you can see, it is less than 8. Let me take another point. Let's say let me take maybe 4. Let me take 4. Then let me draw a vertical line, and from there let me draw a horizontal line. So this is f of 4. Again, as you can see, it is less than 8. So let me take a point less than 3 maybe. Let's say, let me take it, normally we take points very close to 3, but this time around, since to draw it properly in the graph, I'm taking slightly points which are slightly far away from 3. Let's say, let me take 2. Let me take 2. Then let me draw a vertical line, and from there let me draw a horizontal line. So that is f of 2. Okay, as you can see, whatever points you take close to 3, that means f of 2 is less than f of 3, f of 3.5 is also less than f of 3, and f of 4 is also less than f of 3. In fact, f of 3 is the maximum, isn't it? Now, even if you take any other point, let's say if you take if you consider f of 2.9, that will also be less than f of 3. And if you consider, let's say, f of 3.01, that will also be less than f of 3. If you take, let's say, f of 3.6, that will also be f of 3. So from this, what you observe is f of 3 is the maximum, isn't it? F of 3 is the maximum, is the highest in this locality. For example, if you consider this part of the x-axis, f of 3 has the maximum value, isn't it? In fact, here this 8 is actually the maximum, local maximum value. This 8 is called as the local maximum value. It is called as the maximum value, as you can see, is the highest there than any other, like for example, f of 2 or f of 3.5, f of 4 is the highest value, highest y value, and it is called as a local maximum value because maybe in that locality it is highest. Maybe when you extend the curve, you will see that you will get some other maximum value, but in that locality, and I'll explain it maybe with another diagram, but in that locality, I'm talking about this locality, in this locality, that 8 is the maximum value. And we say at x equal to 3, we get a local maximum. We say that at x equal to 3, we get a local maximum. Okay, so very, very simple. So let us now let us again learn more about this particular part of the curve. Okay, so let us look at the diagram again. Now we learned that f of 3, I mean, it's obvious that f of 3 equal to 8, and this 8 is the local local maximum value, isn't it, students? And at 3, when x is 3, we get the local maximum value because it is the maximum in that locality. Okay, now let us look at the behavior of the graph close to 3. You can see that before 3, the function is increasing, isn't it, students? For example, look at the part of this part of the curve. The function is increasing, isn't it? For example, here in this part of the graph, as x becomes bigger and bigger and bigger and bigger and bigger, f of x also becomes bigger. It also becomes bigger and bigger and bigger and bigger, isn't it? So I can write that f of x is increasing in that locality. Let me take it as, let's say, let me take it as 0.8. Okay, let's say in that locality, f of x is increasing here. Okay, let me do this. Now look at the behavior of the curve after 3. Okay, I'm talking about this point. I'm talking about this part of the curve. Here it starts decreasing, isn't it? For example, as x becomes bigger and bigger and bigger and bigger, f of x becomes smaller and smaller and smaller. Okay, so basically here in this locality, sorry, in this particular interval, the function is decreasing. I will say f of x is decreasing. F of x is decreasing here. F of x is in this interval. Okay. Now what about at 3? What happens at 3? Let's say here at the summit. What happens there? Here the function stops increasing, right? Like it is increasing, and when it comes here, it stops increasing. And after that, when it passes 3, it starts decreasing. So at 3, it ceases to increase or decrease, right? Okay. Now let me ask you, what do you think, what will be the value of, let's say, if you want f dash of 2 students, will it be positive or negative, or will it be equal to 0? What about f dash of, let's say, 2.1? What about f dash of, let's say, 2.9? What about f dash of 2.99? What about f dash of 2.999? So what about these values? Will they be positive or negative or 0, students? Okay, it will definitely be positive, isn't it? I hope you remember the increasing and decreasing functions. I have explained in detail in that particular video. So all these values will be positive. Now you might wonder why. Why, sir? Okay, can you please recap? Why are they positive? Okay, let me explain it. Let us say, let me take 2.5. Let's say, okay, let's say I'll erase this part. Okay, let me draw the curve again. Okay, let's say I take let me take 2 here. Let me take 2 here. Say this is 2. So what is the meaning of f dash of 2? Very simple. F dash of 2 means slope of the tangent, right? Now which tangent are we talking about? We are talking about the tangent which is drawn at this point. For example, let me draw a vertical line, draw a horizontal line, and at this point you draw a tangent. At this point you draw a tangent, and that tangent has a slope, and that slope is f dash of 2. Now we know that this particular line, this line has a positive slope, isn't it? So definitely f dash of 2 also has to be positive. Likewise, if you take any point here before 3, and then draw a tangent at the curve near that point, then definitely the slope will be positive, right? So the function is increasing before 3, and it means that f dash of x is positive, right? Okay. Now what about, let's say after 3, let me take points after 3, f dash of, let's say 3.1, f dash of 3.14, let's say f dash of 3.29. So all these values, will they be positive or negative or 0, students? Definitely they will all be less than 0. They will all be negative. Okay, right? Because the function is decreasing. Okay, let me explain it once more. Let's say, let me take a point 3.5, say 3.5. Let me take 3.5. So what is the meaning of f dash of 3.5? F dash of 3.5. It means, let me draw a vertical line. At this point, I'll draw a tangent. And the slope of this tangent is f dash of 3.5. Now we know that for this particular line, the slope will be negative, isn't it? So that definitely f dash of 3.5 is less than 0. Okay, so it's very clear. Now what about f dash of 3? What about that? Now we all know that f dash of 3 means this point, at this point I draw a tangent, and the slope will be f dash of 3. Now we all know that this is a horizontal line, so definitely the slope has to be equal to 0. So f dash of 3 equal to 0. Okay, so let us sum it up. Okay, so what we get is f dash of x is more than 0 if x is less than 3, and f dash of x is equal to 0 if x is 3, and f dash of x is less than 0 if x is more than 3, isn't it? So before 3 the function is increasing, so that's why f dash of x is more than 0, and at 3 it stops increasing, so that's why the slope is 0, f dash of x equal to 0, and after 3 the curve starts decreasing, the function starts decreasing, so that's why f dash of x is less than 0. So if you put it on a number line, okay, so it will look like this. If you put it on a number line, so at 3, so before 3 f dash of x is positive, so after 3 f dash of x is negative. So when you actually see this line, students, you should imagine the curve. Before 3 f dash of x is positive means the curve is increasing, the curve is increasing like that, and at 3 it stops, and after 3 the f dash of x is less than 0 means it starts decreasing. So something like this. Okay, you should be able to imagine the curve. Now this point, the point that we're talking about here, that is 3, 8. This point has this particular, I mean, these are the coordinates of the point, but this point has a name. The name is, it is a stationary point. A stationary point. Okay, to put it easily, a stationary point is a point where f dash of x equal to 0, where the slope of the tangent is equal to 0. So this point at the summit is actually the stationary point. So I hope this maximum, local maximum is clear. So let us go and learn about local minimum. Okay, now look at this diagram, students. You can see I have drawn a part of a curve y equal to f of x, and you can see here I have marked a point. So this point that you see is this point that you see here is 4, 1. So basically it means f of 4 is equal to 1. Okay, now let me take a point close to 4 and then find its image. Okay, let's say f of 4.1, right? So now will it be bigger than f of 4, students? Okay, let me take f of 4.4, say this. Okay, let me take 4.3 because it is easier to represent in the diagram. Let me take f of 4 point, let's say 3. So let's say this is f of 4.3. This is 4.3. This is 4.3. So let me draw a vertical line. Let me draw a horizontal line. So this is f of 4.3. As you can see, f of 4.3 is definitely more than f of 4. Okay. What about let's say f of 4.9? Let me take it. Let's say this is 4.9. Let's say this is 4.9, and draw a vertical line. From there, draw a horizontal line. So this is f of 4.9. Again, as you can see, f of 4.9 is also greater than f of 4. Okay, now let me take a point less than 4. Let me take, let's say 3.2. Let's say this is 3.2. This is 3.2. Okay, again let me find f of 3.2. So for that you need to draw a vertical line and then draw a horizontal line. So basically it's almost like same. It looks same. F of 3.2. So as you can see, f of 3.2 is also greater than f of 4. Okay. In fact, if you take any point close to 4, f of 4 will be the smallest value, isn't it, student? f of 4 will be the smallest line. So from this, what we understand is this one that you see here is a minimum value. Not just a minimum value, it is the local minimum value. That means in that locality, in this locality, right? In this f of 4 is the smallest. So local minimum value. And at x equal to 4, when x is 4, we get the local minimum value. And again, let us look at the behavior of the curve before and after 4. But finally, we can sum it up saying that in this locality, f of 4 is the minimum value, right? Local minimum value. Good. Okay, let us look at this now. Now, if you see here, before 4, that means I'm talking about this part. Before 4, the function is decreasing, isn't it? That means this part of the curve, the function is decreasing. What does it mean? That means as x becomes bigger and bigger and bigger and bigger, f of x becomes smaller and smaller and smaller and smaller. Right? So I can write that f of x is decreasing. F of x is decreasing here. What about after 4? After 4, you can see that means this part of the curve, the function is increasing, isn't it? Which means as x becomes again bigger and bigger and bigger and bigger, f of x also becomes bigger and bigger. Okay, so I can say that f of x is increasing. Now, where is it increasing? F of x is increasing here. F of x is increasing here. Right? Okay. So now, what can you say about, let's say, f dash of 3.8, f dash of 3.84, let's say f dash of 3.9, f dash of 3.98. What can you say about this value, students? I'm sorry, the numbers don't look clear. This is 8, this is 8.4, this is 3.98. Okay. Now, will they be positive, negative, or 0? Definitely they will all be negative. They will all be negative, isn't it? I hope you understand why it is so. And so they are all negative. What about, let's say, f dash of 4.1, f dash of 4.16, f dash of, let's say, 4.3? All these values will be positive, isn't it? Strictly greater than 0. Okay. What about f dash of 4? F dash of 4 will definitely be equal to 0. So before 4, their derivative is negative. After 4, the derivative, that is f dash of x, is positive. Now this point that you see here, this point that you see here, okay, let me mark it with this color. This point that you see here, this point is, as I mentioned earlier, a stationary point. A stationary point. Now, why is it a stationary point? Very simple, because f dash of x is 0. So, stationary point is a point where f dash of x equal to 0. So, in fact, if you look at it, before 4 the function is decreasing. At 4 it stops decreasing, and then after 4 it starts increasing. So 4 is a point, I mean that 4 comma 1 is the point where the curve, the function ceases to increase or decrease, right? So local maximum and local minimum. Now let me explain why do we use this word local minimum. Okay, can a curve have more than one local maximum value, or can they have more than one local minimum value? Definitely. So let us see that now. Okay, so let us look at this diagram, students. As you can see, I have plotted 3 points in the x-axis, 3, 5 and 6.5. Now let's say f of 3 is let's say 10. Okay, and okay, this is y-axis and this is x-axis. Okay, so f of 3 is 10, and let's say f of 5 is let me draw this. Let's say this is 1. Okay, so f of 5 is 1, so f of 3 is 10 and f of 5 is 1, and f of 6.5 is, let's say, 8. So f of 6.5 is equal to 8. Now as you can see, if you look at the whole interval, that means this interval, f of 3 is the maximum value, isn't it? Because 10 is the maximum. But 6, that is 8, that you see here, is actually the maximum in that locality. Like there, this is the maximum, isn't it? This part, f of 6.5 is the maximum. So I would say that in this locality, 8 is the maximum value. So I'll call it as local maximum value. Okay. So now this is also a local maximum value. So this function, this part of the curve, has two local maximum values. What about 1? Very simple. 1 is a local minimum value. Okay, so a function definitely can have more than one local maximum value, and they can also have more than one local minimum value. And again, it is not necessary that every function should have a maximum value or a minimum value. We'll see that later. Okay, now another question. Can a local minimum value be greater than a local maximum value? Okay, let me repeat the question again. Can a local minimum value be greater than a local maximum value? Now you might wonder, how so? Like, how come a minimum is bigger than maximum? Always the maximum is bigger than minimum. So how come a minimum is bigger than maximum? So let us see that. Okay, now look at this diagram, students. As you can see, there are two maximum values. That means I get it here, here and here, and you get two local minimum values using these points. Okay, now look at this the value 4. Okay, let me draw a line. Let's say this is 4 again. So basically f of 4 is also 4. So this is a local minimum value, right? Now let us look at f of 8. Again, draw a vertical line. So let's say this is 3.7. So f of 8 is 3.7. So this is a local maximum value, right? Now you might wonder, how come, sir, a local maximum value is 3.7 and local minimum value is 4, which is more than 3.7. So definitely it can happen. As I mentioned earlier, a local minimum value need not be always smaller than a local maximum value. In some cases, they will be greater than a local maximum value. So it is possible, right? Okay, so look at this diagram, students. Okay, can you please tell me what are the local maximum values and what are the local minimum values, and how many stationary points that you can see here, which is quite easy to find. How many stationary points and what are they? Okay, first, the local maximum values are 5 and 7, isn't it? They are the local maximum, values. Okay, what about the local minimum values? Very simple. This one, this -5 and -2. These two are local minimum values. Okay, and what are the stationary points? These are the stationary points: 1, 2, 3, and 4. So these are the stationary points. So there are 4 stationary points that you can notice, right? Good. Okay, now look at this graph, students. This is nothing but y equal to x cubed. Now, if you see here, before 0, the function is increasing, right? In fact, this part, the function is increasing. Here, the function is increasing. And even after 0, no, at 0, what happens is, okay, maybe at 0, what happens is it stops increasing. Okay, it doesn't look like it. Let me draw it properly. So, draw it properly. Let's see. Okay, so sorry. Okay, what I do is it comes like this, and it's like this, As you can see, at 0, if I draw a tangent, that means a tangent like this is the tangent actually, then the slope will be 0, right? Slope is equal to 0. So here, this is 0. F dash of 0 is actually 0, right? So before that, before 0, the function is increasing. That means here the function is increasing, and after 0, again it is increasing. That means this part, it is increasing. So before 0 it increases, after 0 also it increases, but at 0 it stops increasing, right? So definitely here, this point that you see here is definitely a stationary point because f dash of x is equal to 0. But before and after that, the sign doesn't change. The sign of the derivative does not change. It is positive. Both f dash of x is positive. F dash of x is positive both before and after 0. So this point, that means this point that you see here, is called as a stationary point, definitely, because f dash of x is 0, but it is called as a point of inflection. Point of inflection. It is called as a stationary point of inflection, but the important thing that you need to notice is it's a point of inflection. So what do you mean by that? That means before and after that point, the function does not, the derivative does not change its sign. Okay, or you can say that at that point, even though the first derivative is 0, that means f dash of x is 0, still it is neither a peak nor a drop. Okay, so the sign of the derivative does not change. So what I'll do is, in another video we will see it in detail, like what do you mean by a point of inflection. And there are in fact 2 types of points of inflection. One is stationary point of inflection and another one is non-stationary point of inflection. So when you learn about points of inflection, we'll also learn about the second derivatives. So I think I'll have it in another video. So I hope you're clear about the local maximum value, local minimum value, and the stationary point of inflection. So let us solve some problems now. Okay, let us look at this problem. Y equal to x squared minus 6x plus 10. As you can see, this is a quadratic function. So definitely the graph, you'll get a parabola. And since the coefficient of x squared is positive, you'll get a parabola like this, like a parabola which is open at the top. Okay, so as you can see, you will actually get a minimum value. So my objective is to find whether this function has any local maximum or local minimum value, and I would also look to find the stationary point. Obviously, first you find the stationary point, then only you can find the local maximum or minimum value. Now, I can do it in two ways, right? So let me first use the first way, that is, let me sketch the graph. How do you do that? Very simple. I'll draw the y-axis and I'll draw the x-axis. Okay, so what I'll do is I'll complete the square. Okay, I hope you have watched my video on how to complete the square. So this can be written as x minus 3 the whole square plus 1, right? What it means is the vertex of this parabola will be 3, 1. So let's say this is 3 and this is 1. So this is the vertex of the parabola. So the parabola will look like this. Okay. Now, where does it cut y-axis? Very simple. In this, put x as 0. Put x as 0. You'll get the y-intercept. So this point is nothing but 10. Right? The y-intercept is 10. Okay. As you can see very clearly, you have a maximum value at 3. When x is 3, we have a maximum. I'm really sorry. You have a minimum value. So when x equal to 3, we have a local minimum value. We have a local minimum value, and that is nothing but 1. So this 1 is the local minimum value, right? And this point that you hear, that means 3, 1 are the coordinates of this stationary point. And as you can see, before 3 the function is decreasing, and after 3, so here the function is decreasing, therefore f dash of x will definitely be negative, and after 3 the function is increasing. So here it is decreasing, and after 3 it is increasing. So that's all. So this graph has this function has only one minimum value, that is 1, and it does not have any maximum value. Okay, and it does not have any point of inflection as well. Okay, so that's it. Okay, so now let me do it using the second way. Okay. Okay, look at this function, students. Now, this is again a quadratic function, so definitely you'll get a parabola. Now the coefficient of x square is negative. As you can see here, it is negative. So therefore, you'll get a parabola like this. That means you will actually get a local maximum value. So again, let me do it using both the ways. First, by sketching the graph. So what I'll do is I will take -1 common. So this will become x squared minus 2x minus 3. So if I Okay, let me erase this. So when you actually complete the square, you'll get something like this: minus of x minus 1 the whole square plus 4, right? So let me draw the y-axis and the x-axis. This x and this is y, and you can see for this parabola the vertex is 1 comma 4. So let's say this is 1 and this is 4. So this is 1 and this is 4. So this is the point, and this is how the parabola will look like. Okay. Now, as you can see, let me write it clearly. So this is 1 and this is 4. So this point is 1 comma 4. Okay. So you can see before 1 the function is increasing, and after 4 the function is decreasing. I'm sorry, before 1 the function is increasing, and after 1 the function is decreasing, and at 1 you get the peak, right? You get the peak at 1. So this point that you see here is a stationary point in fact. Okay, and this 4 that you see here is actually the local maximum value, right students? Local maximum value. So you get a local maximum value of 4 when x is 1, right? So this is how you can find the answer by sketching the graph, okay, of the function. Now what about without doing it? What about the second way? Let us see that. Okay, so what I'll do is I've written the function here. So first find the first derivative, f dash of x, which is 0 plus 2 minus 2x. My next objective is to find the stationary point. So for that you need to equate the first derivative to 0. So you get x equal to 1. So at 1 you get a stationary point. So what I'll do is I'll draw a number line and I'll mark 1 here. Then I'll take a value less than 1, slightly less than 1, and substitute in the first derivative. So let me take 0.8. So f dash of 0.8 is nothing but 2 minus 2 into 0.8, which is nothing but 0.4, so positive. So here before 1 the first derivative is positive. It means before 1 the function is increasing. Okay, now let me take value greater than 1. Let me take, let's say, 1.2. So f dash of 1.2 will be 2 minus 2 times 1.2, which is actually minus 0.4, again negative. It means negative. So I get f dash of x less than 0. That means the function is decreasing. So that means the before 1 the function is increasing, and after 1 the function is decreasing. So this point will be 1 comma something. Okay, so definitely, as you can see, you get a peak. That means you get a local maximum value. Now how do I find that local maximum value? Very simple. Substitute it in the original function, the value of x, replace x with 1. So I'll get f of 1 equal to 3 plus 2 minus 1, so which is actually 4. So this is the local maximum value. Okay, this is the local maximum value. Very, very simple. Without actually sketching the graph, I have found the local maximum value. So let us see one more problem. Okay, let us look at this problem. F of x equal to x cube. Now if you recall, we found out that it doesn't have any local maximum or minimum value. In fact, it has a point of inflection. Okay, so we drew the graph of x cubed, and then we found out earlier in the same video. So let me do it now. Let me find that fact without actually sketching the graph. So let me find the first derivative, that is f dash of x equal to 3x square. Then next I would like to find the stationary point. For that I'll equate the first derivative to 0, which will give me x equal to 0. I'm sorry, x equal to 0. So I'll draw a number line. I'll mark 0 here, and I'll take a value before 0. Let's say minus 0.5. So f dash of minus 0.5 is 3 times minus 0.5 the whole square, which is actually positive. So here f dash of x is positive. So let me take a value after 0. Let me take 0.1. So f dash of 0.1, which is nothing but 3 into 0.1 the whole square, again positive. So f dash of x is again more than 0. As you can see, before 0 the function is increasing. At 0 it stops, and again it's increasing. So basically you get a point of inflection. Okay, if they ask you to find the coordinates of point of inflection, substitute that x equal to 0 here. So f of 0 equal to 0 cube, that is also 0. That means 0 comma 0 are the coordinates of the stationary point of inflection. Okay, now let us do some let us find the maximum minimum values, if they exist, of a cubic function. Okay, so f of x equal to x cubed minus 6x squared plus 8. So I'm not going to sketch the graph now of this function. So I'm going to do using first derivative method. So find f dash of x. So f dash of x is derivative of x cubed is 3x squared minus 6x squared will become 12x plus 0. Okay, so this is the first derivative. Now I will find the stationary points. So for that I'll equate the first derivative to 0. So which basically means x squared minus 4x equal to 0. So I'll get x, I take x common, x into x minus 4 equal to 0, which means x is either 0 or 4. Okay, so that means 0 and 4. At 0 and 4 I get stationary points. So now I'll draw the number line. I'll mark 0 and 4 here. I'll take 0 here and I'll take 4 here. Now let me take a value. Now I would like to know the behavior of the function, whether it is increasing or decreasing before 0 and between 0 and 4 and then after 4. And because that will give me an idea as to whether this points, the x value 0 and 4 will give me a local maximum value or a local minimum value, or whether it will give me a point of inflection. Okay, so let me take a value less than 0. Let me take let's say minus 0.1. Okay, so you get f dash of minus 0.1 is nothing but substitute in the first derivative. So 3 into minus 0.1 the whole square minus 12 into minus 0.1. So basically you will get a positive value, isn't it? So you can check using a calculator, you get a positive value. So f dash of x is more than 0. Very good. Now let me take a value after 0. So let me take f dash of 0.1. f dash of 0.1 equal to 3 into 0.1 the whole square minus 12 into 0.1. So basically you will get, okay, you will get 0.03 minus 1.2, which is basically a negative value. So you will get f dash of x is less than 0. That means if you take any x value between 0 and 4 and substitute in the first derivative, you will always get a negative answer. Now let me take a value more than 4. So let me take, let's say, 4.1. So f dash of 4.1 equal to 3 into 4.1 the whole square minus 12 into 4.1. Now if you use a calculator and check, you will understand that, okay, 3 into if you use a calculator, you know that you will get a positive value. So here f dash of x is more than 0, right? Okay, so now look at this. From this, what do we understand? Before 0, f dash of x, I'm sorry, f dash of x is positive before 0. So now before 0 f dash of x is positive, that means it is increasing, and after 0 f dash of x is negative, that means it decreases. That means this point is 0 comma something, you get a maximum value. Now 4, look at 4 now. Now before 4 the function is decreasing, so function is decreasing, and after 4 the function is increasing. That means at 4 you get a minimum value. Let's say this is 4 comma something, you get a minimum value here, right? So how do you find that minimum value? Very simple, substitute in the original function. So f of 0 is 0 minus 0 plus 8 equal to 8. So this is the local maximum value. Okay, let me find f of 4. F of 4 is 4 cubed minus 6 into 4 squared plus 8. So you'll get 64 minus 96 plus 8. So basically, which is nothing but 72 minus 96 is minus 24. So this is the local minimum value. Okay, so this function has a local maximum value, which is actually 8 when x is 0, and it also has a local minimum value when x is 4. That local minimum value is nothing but minus 24. And it also has two stationary points, one at 0 when x is 0 and another stationary point when x is 4. Okay, now this we did it without sketching the curve. So what I'm going to do, for your benefit, to make you understand this better, I'm going to sketch the curve. Okay, I'm going to use the calculator to sketch the curve to cross check whether what we have found is correct or not. Okay, so I use my calculator to sketch this curve. I use my GDC. As you can see, you get a local maximum value at which is 8 when x is 0, and you also get a local minimum value which is actually minus 24 when x is 4. So basically whatever we did is correct. Okay, fine. So let us see a last problem, one more problem, and with that we shall wind off. Okay, now this is the problem. So I can do it two ways. I can either, so first thing is I need to find whether this particular cubic function has a local maximum or minimum values, and if they are existing, then we need to find them. But first, we always find the first derivative. So either I can use the product rule here, I can just simplify, open the bracket and then differentiate. So let's say in this case, I just open the bracket, and if you simplify, you will get x cubed, okay, minus x squared minus 4x plus 4. So this is what I will get if I expand it. So first find f dash of x. F dash of x is equal to, you will get 3x squared minus 2x minus 4. Okay, now I'll equate this to 0 to find the stationary point. So 3x squared minus 2x minus 4 equal to 0. And as you can see, when you can't factorize it, in the sense that you won't get any integral values as the solution of this equation. So definitely you have to use a calculator, the quadratic formula, or you can use the calculator to find the x values, to find the solutions of this quadratic equation. Okay, so we'll get x as, let me write in three significant figures. We'll get x as either 1.54 or minus 0.868. Okay, now let me draw a number line now. We represent both the points here. So I'll write minus 0.868 and I'll get 1.54 here. So let me take a value which is less than minus 0.868. So let me take minus 1. So f dash of minus 1 is, if you substitute in the first derivative, you'll get 3 plus 2 minus 4. So you'll get basically f dash of x will be positive before this point. After this point, let me take, let's say 0. So f dash of 0 will be 0 minus 0 minus 4. So negative. This is positive, this is negative. So f dash of x will be negative. And after 1.54, let me take a point, let's say, let me take 1.6, or let me take f2 also. So f dash of 2 will be 3 into 2 square minus 2 into 2 minus 4. So basically you'll get 12 minus 4 minus 4, which is 4 positive. So f dash of x is positive. Okay, now this will give me an idea as to whether we'll get a maximum or minimum value. Now, as you can see, before this point, I'm sorry, minus 0.868. Now, before this point, the first derivative is positive. That means it is increasing. After this point, the first derivative is decreasing. I'm sorry, first derivative is less than 0, therefore the function is decreasing. That means at this point you get a local maximum value. So that is f of minus 0.868. So substitute this value here and use your calculator to find the answer. So this will be the local maximum value. Okay, now look at 1.54. Before that, the first derivative is negative, that means the function is decreasing, and after that the first derivative is positive, therefore the function is increasing. Therefore you get a minimum value. So to find that f of 1.54, you substitute in the original function again, you will get a local minimum value, right? In fact, you can even sketch this, find how you can use the graphic display calculator to sketch the graph, and then you can cross check whether what you've done is correct or wrong. Okay, so I hope you understood the concept of local maximum and local minimum value, and so see you soon, students. Thanks for watching this video.